In section 9.2, I'm going to do some numerical examples involving objects on slanted surfaces. Here we have a 50-kilogram student climbing a rock face at a constant speed. We're going to neglect drag and any friction impeding her motion, and we need to find the force that the student generates up the hill and the normal force that's acting on the student. So to start with, we're going to draw a free body diagram showing the forces acting on the student. We'll have the weight force that's acting down, but since we are going to have a coordinate system aligned with the slanted surface, we have to break that weight force into its downhill and normal components. There's going to be a normal force acting away from and perpendicular to the hill. And there's going to be an applied force up the hill, and that's what we're trying to find in part A. Because the problem states that the student is climbing with a constant speed, that is going to imply that the forces acting on the student are balanced. And so we know that applied force, the force that is generated by the student, is going to have to equal the downhill component of the weight force. And from last lecture, we learned that the downhill component of the weight force is the weight times the sine of the ramp angle theta. To find the weight, we simply have to take the mass that's given as 50 kilograms times g, which we're using a value of 10. So there is 500 Newton weight times the sine of our angle, which is 65 degrees. And that's going to give us our answer, 453, and that's a force, so it is measured in newtons. For part B, we have to find the normal force acting on the student. Well, the normal force is going to have to equal the normal component to the weight. And we know from last lecture how to figure that out. You take the weight and multiply it by the cosine of the ramp angle theta. We'll plug in our numbers. The weight is 500 newtons. We're going to multiply that by the cosine of the angle, which is given as 65 degrees. And when we crunch the numbers, we get 211. And normal force is a force, so it's measured in newtons. Okay, one more. Here we have a 4-kilogram cart rolling down an incline with an acceleration of 5 meters per second squared. We're going to neglect friction and drag. We need to find the net force on the cart, and we need to find the angle theta. So to start with, again, we're going to draw a free body diagram showing the forces acting on the cart. We'll have the normal force acting normal to, aka perpendicular to the surface of contact. And we'll have the weight force. Now, those are the only two forces that are acting on the cart, but we have to split that weight force into its downhill and normal components because we have a coordinate system that lines up with the incline. So to find the net force, it's very straightforward. We're going to use Newton's second law. Newton's second law says that the net force acting on an object is equal to its mass times its acceleration. We're given the mass as 4 kilograms. We're given the acceleration as 5 meters per second squared. And so the net force is going to be 20 newtons. And we should note that the the net force rather is down the incline. That's the direction of the acceleration, so that's the direction of the net force. The downhill component of the weight is the only force acting in that direction. Therefore, the net force is equal to the downhill component to the weight. Well, the downhill component to the weight is just the weight times the sine of theta. Well, if I know the net force and I know the weight, then the only thing that I'm missing in this equation is theta. So plugging in values, the net force is 20. The weight is going to be 4 times g. G is 10, so 4 times 10 is 40. If I divide each side by 40, I get sine theta equals 20 divided by 40, which of course is a half. And when you enter into your calculator inverse sine of 1/2, you get 30 degrees. Therefore, the ramp angle is 30 degrees.